So for the rest of this chapter, we'll be looking at how the properties of the elements changes as you go across a period and down any group, all right? And what we're going to see in this section and for the rest of this chapter is the correlation between the electron arrangement of the atoms and their physical properties and the trends that we're going to observe going across a period and down the group. So what I want to say here, just to start things off, is that it was discovered way back when, I don't remember exactly the year, but a long time ago, that if you arrange your elements according to their increasing atomic mass, then after so many elements, the properties tend to repeat themselves, all right? And this was first discovered by Mendeleev. He's the one with credited with coming up with the first version of the periodic table based on that particular observation. Back then, however, they did not know exactly the electronic arrangement of the atom. In fact, the structure of the atom was still a mystery. Nobody knew back then. All they knew was that the properties vary according to their increasing atomic mass. The concept of atomic number didn't come about as a result because back then they didn't know anything about protons, which is what we use to define the atomic number. However, after many years, the atom was probed into, the different particles were discovered, and now we have our current understanding of how the electrons are arranged, and we can now see the correlation between the trends that we're about to discuss and the electronic arrangement. So that's what we're going to discuss in this particular chapter, or this section of this chapter. All right, so when we're talking about properties, we're talking about basically any properties that we can identify: melting points, boiling points, hardness, density, physical state, and also chemical properties, the type of reactions that elements will undergo. So what we're going to start off by looking at is the variety, or how the atomic size varies as you go across a period and down a group. So let's first define what we mean by the atomic radius, okay? So here's a definition of the atomic radius of an atom. It is half the distance between the nuclei of two atoms not bonded to each other, and that is what the atomic radius is. It is half the distance between the nuclei of two atoms not bonded to each other. Now, there are other definitions. For example, you have what is known as a covalent radius, which is half the distance between the nuclei of two identical atoms joined in a molecule. So if we have two atoms that are covalently bonded, then the distance between the nucleus, or half the distance between the nucleus or the two nuclei of the separate atoms, would be the covalent radius. All right, so basically, as you can see here, for example, I'm not sure what molecule this is. The distance between the two nuclei is 266 picometers. So therefore, the covalent radius, by this definition, would be 133 picometers. And then we have what is known as a metallic radius, which of course is exclusively related to metals. It is half a distance between the nuclei of adjacent atoms in a solid metal. So it's kind of similar to the covalent radius, but only applies to metals. Okay, so let's talk about the atomic radius and the variety, or the trend, in terms of how it varies as you go down a group. And as stated here, this is what is observed, and there are no exceptions to this really. The atomic radius increases from top to bottom within a group. So as you go down a group, the atomic radius increases. And this is related to the value of n, which of course would be, in this case, the principal quantum number, or representing the shell, and more specifically, the valence shell, right? As the valence shell n value increases, then basically that's what we observe. The atomic radius increases, all right? And that's because the value of n relates to the distance of the electron, the valence electron, from the nucleus. So that's what happens as you go down a group. Now, going across a period from left to right, what you'll find is that the atomic radius will decrease going from left to right. Now, why is that so? Well, it has to do with what is called the effective nuclear charge. The effective nuclear charge experienced by the valence electron. So just as an example here, let's say we look at the sodium atom here, and this representation of the sodium atom, of course, has 11 protons, because that's the atomic number. And then within the first and second shell, you have a total of 10 electrons, right? So those are the core electrons. Now, outside of that, you have the valence electron, and there's only one of them in the 3s orbital of the third shell, all right? So basically, this one electron here, well, firstly, let me say this. So the atomic size is pretty much determined by the distance between the nucleus and the valence electron, right? So basically, this valence electron here will be exposed to a nuclear charge of about 11, but it is also exposed to electrons in the core region here, and there are 10 electrons, right? So you have 10 negative charges here, basically effectively canceling out 10 of the 11 plus charge of the nucleus. So therefore, the nuclear charge felt by the valence electron here will be a net attraction of +1, right? So that's as far as the sodium is concerned. Now for the next element to sodium, going left of that period would be magnesium. And in the case of magnesium, the nuclear charge increases by 1 from 11 to 12, but the number of core electrons is still the same, 10. So therefore, the nuclear attraction, the net attraction that the valence electron here, in the case of magnesium, and there are two of them, will be +2. So basically, magnesium has a greater effective nuclear charge compared to the sodium atom. And the result of that is that the valence electrons, in the case of magnesium, will be pulled closer to the nucleus, and therefore the magnesium atom will have a smaller radius compared to the sodium atom. And basically that trend will continue right across that particular period, all right? So going from left to right of any period of the periodic table, the atomic size will decrease, and that's because the effective nuclear charge experienced by the valence electron will increase, and therefore those electrons, as well as the other electrons in the atom, will be pulled closer to the nucleus, and therefore the atomic size will decrease as you go from left to right, all right? So that's basically how we can make predictions as to the trends in terms of the atomic size going down the group and across a period. Now, this graph here is a plot for each period of the atomic size as measured by the atomic radius in picometers versus the atomic number. And you see that for the most part, going from left to right of any period, generally speaking, the atomic size decreases. So you can see that for period 2, starting with lithium, right, and ending with fluorine, you see the atomic size decreases. The same is true for period 3, same is true for period 4. There's a slight bump here, slight increase here, and then it goes down. And this is true for period 5 and 6. Again, there are some exceptions here, which I won't get into the reasons why. I'm just covering the general trend, and that is that as you go from left to right of any period, the atomic size decreases, all right? And then this also shows that going from bottom to top, or I should say from top to bottom of any group, the atomic size increases. So if you take group 1A, which consists of lithium, sodium, potassium, rubidium, and cesium, you see that there's an increase in the atomic size as you go down that group. And that is true for elements in group 2 and all the other different groups in the periodic table. As you go down any group, the atomic size increases. So with that said, let's look at this example here. Now what I'm going to do, I'm going to try to work this thing here so that I can share with you guys the periodic table, because we're going to need it in order to answer this question. So the question says, in fact, let me get out of this here and let me go. Okay, so this is the question. Let me get the periodic table in place. Okay, so this is the question. The question says, with reference only to the periodic table, arrange each set of elements in order of increasing atomic mass. So it says increasing atomic radius. So it says increasing atomic radius. So basically what it's talking about here is starting from the smallest to the largest, right? So the first set of elements here is given in A, magnesium, sulfur, and silicon. So we have to locate where the different elements are. Magnesium is here, and then to the right of magnesium is silicon, and then to the right of silicon is sulfur, right? So therefore, since sulfur is the one to the extreme right, sulfur would be the element that would be indicated first. So I'm going to put sulfur first, right, as being the smallest, and then followed by silicon, and then followed by magnesium. All right, so that's the answer for A, right? Sulfur will be the smallest, followed by silicon, followed by magnesium, because they're in the same period, but sulfur is to the right of magnesium. Remember, the atomic size decreases as you go across left to right, so sulfur would be the smallest, followed by silicon, followed by magnesium. Okay, so that's A. In the case of B, they gave you arsenic, nitrogen, and phosphorus. So where's arsenic? Arsenic, 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 arsenic is here, nitrogen is here, and phosphorus is here. As you can see, they're all in the same group, right? So I would say that the smallest in size, now remember, the size increases as you go down the group. So the smallest in size would be nitrogen. So for B, the smallest in size would be nitrogen, followed by followed by phosphorus, and then followed by arsenic. All right? So that's the answer for B. Now let's look at what happens in the case of C. In the case of C, they gave you arsenic, antimony, that's SB, and selenium. So let's see where those elements are located in the periodic table. Okay, so I see selenium here, arsenic here, and antimony is here, all right? So in this case here, we have arsenic, which is in the same period as selenium, but antimony is in the same group as arsenic. So I would say that in the case of C, the one that would be the smallest would be the selenium, right? So selenium would be the smallest, followed by arsenic, because arsenic is to the left of selenium, all right? And then because antimony is below arsenic, atomic size increases as you go down, so therefore antimony would be the largest. So in the case of C, the answer would be that selenium is the smallest, followed by arsenic, followed by antimony. All right, so that's basically the answer for just checking something here. So sulfur, what do I say? Not sulfur, selenium. I know I made a mistake somewhere here. So selenium would be the smallest, followed by arsenic, and then antimony. All right, so that's basically how we do this particular example. So questions involving atomic size trends is basically of this type, where you're given a series of elements and you're asked to place them in order of increasing or decreasing size. Okay, let's see